Good morning, everybody. Is my voice audible? Hello?
Yes, sir.
Okay, all right. So I'm just putting everyone on mute so that I can talk. Uh, at the end of the session, I'll unmute everyone's voices so that if you have any questions, queries, we can answer that. This session is going to last about 30 minutes because that's the limit on Zoom currently. So we'll take this session for 30 minutes. If required, I'll send you an additional link. We can take an additional lecture if required, but I'll try to complete this session within 30 minutes. Okay, so I'm just muting you all. Okay. Well, today we are going to start, rather not start. I've already given you the first video for the 6th unit, which is multivariable optimization. What we are going to do is we are going to just continue with that. We'll do a quick revision of what it is. So revision, we are just going to study the classical method. In classical method, like single variable optimization, there are two things. One is necessary condition and one is sufficient condition. The necessary condition is that if the function of x1, x2 up to xn, that is if function of capital X, which is a function of other small variables, has an extreme point at x is equal to x star, and if the first partial derivatives of f of x exist at x star, then we know that the partial derivatives with respect to each variable should be equal to 0, very similar to the single variable optimization. That is, the first partial differentiation should be equal to 0. After that, so we have the sufficient condition. In sufficient condition, what do we have is at extreme point, if the Hessian matrix is positive definite, then it is a relative minimum. It at extreme point, if the Hessian matrix is negative, then it is a negative definite. Yeah, someone is trying to write something. Please do not do that. The third point is if Hessian matrix, if at an extreme point, if the Hessian matrix is neither positive nor negative definite, then it is a saddle point. So we'll look at all these three things one by one. What is Hessian matrix? We had done that. Hessian matrix is a matrix of second order partial differences. So basically, if you take partial differences of, if you take the partial differences, that is dabba f square upon dabba x1 square, dabba f2 square upon dabba x1, dabba x2, and so on. And if you write a square matrix of this, that is nothing but your Hessian matrix that we had done. After that, moving forward, you know what is a Hessian matrix? We can always derive the Hessian matrix. Hello? Hello?
Yes, sir, we can listen your voice.
Okay, so we'll just restart it. I'm going to mute everyone again. So we discussed, just going back, we discussed what are principal minor matrices. So if H is nothing but a square matrix of 9, let's say 9 different terms. So you have A11, A12, A13, A21, A22, A23, A31, A32, and A33. Then the first Hessian matrix is nothing but the first square matrix of the diagonal, that is A11. After that, you take the second 2 by 2 matrix, that is A1, A11, A12, A21, and A22. After that, the next Hessian matrix will be the entire Hessian matrix. So basically, you go diagonally taking the square element at a time. So that is what is nothing but your principal minor matrices. Okay, so with that, we'll move forward. So we have something called as positive definite and negative definite. We want to see what is positive definite and negative definite. So now what we do is, if all the determinants of all principal minor matrices are greater than 0, then the matrix is said to be positive definite. So the minor matrix that we have, H1, H2 and H3, we find the determinants of them. If everything is greater than 0, then we see that the Haitian matrix is positive definite. After that, if all the determinants of the principal minor of a matrix alternate between negative and positive. So first I have said negative and then I have said positive. If they alternate between negative and positive, then the matrix is said to be negative definite. So in other words, you can write this form in mathematically as well. Minus 1 raised to k, determinant of hk is greater than 0, where k is 1 to up to n. So for every odd number, you will automatically have this negative sign coming in. So if it is negative first and then positive, negative, positive, and so on, then we say it as negative definite. Right. So the third one is that I'm not written here, but so if it is neither positive definite or neither negative definite, we call it as indefinite, and that point is nothing but a saddle point. So now let us solve this numerical together. If you have your notebooks with you, if you have your pens, it would be nice. You can solve this problem with me so that you will be able to understand. The question is, find the extreme points of the function f of xy is equal to x square y minus 2xy square plus 3xy plus 4, and determine the nature of these points as well. So this is the question. You can write down. If you have notebooks, please write down so that we can solve this together. Okay. Moving forward, we'll start with the solution. The first thing that you do is, we want to use the necessary condition to find the extreme points. So what do you do is, you find da by f upon da by x, that is the first differential, that is equal to, it comes with as 2xy minus 2y square plus 3y is equal to 0. Okay, so what I can take is, I can take y common here. So this becomes y into 2x minus 2y plus 3 is equal to 0. So in other terms, I can say either y is 0 or this term is equal to minus 3, or this term is equal to 0. I'm taking 3 to the other side. This becomes minus 3. And this was the first differentiation. You can also differentiate with respect to the second variable, that is y. So da by f upon da by y will become x square minus 4xy plus 3x is equal to 0. In other terms, if I take x common, I have x minus 4y plus 3 is equal to 0. Or in other words, either x is 0 or x minus 4y plus 3 is equal to 0. Now to find critical points, what I'm going to do is, I'm going to take one term with respect to other. So for example, what I'm doing is, what I'll take is, I'll take this x and y. I'll take this x and this term. I'll take this term along with this term, and I'll take this term along with this term. Okay, so taking such 4 points, we will be able to find the extreme point. So the first point will be x0, y0. The second point will be x0 and 2x plus 2y is equal to minus 3. Put x is equal to 0 because we have taken that, and you'll get the value. In the third condition, you're putting y0 and this condition, so put y is equal to 0, you'll get the value for x. And in the fourth condition, you're taking these 2 points. You can solve them simultaneously and get the values. So to show what happens, I'm going to the next slide. I'll erase this. So the critical points will be, so first one, like I said, x is equal to 0, y is equal to 0. After that, x is equal to 0 and 2x minus 2y plus 3 is equal to 0. So now x is 0, so I'm putting x as 0 here. So this becomes minus 2y plus 3 is equal to 0. In other words, y will become 3 by 2. So the second critical point is 0 and 3 by 2. The third point, y is equal to 0 and x minus 4y is equal to minus 3. So now y is equal to 0, so I can put y is equal to 0 here. This term becomes 0 and x you will directly get as minus 3. So the third critical point is minus 3 comma 0. The fourth one is the two other conditions. We are taking them simultaneously. 2x minus 2y plus 3 is equal to 0 and x minus 4y plus 3 is equal to 0. So now if I solve them simultaneously, I get the values of x and y. So x will be equal to minus 1 and y will be equal to 1 half. So now we formulate the Hessian matrix and the principal minor matrices. How do we do that? First we start finding the second differentials. So dabba f square upon dabba x square, if I find that, it comes up to 2y. If I find dabba f square upon dabba y square, that will come as minus 4x. And if I find dabba f square upon dabba x dabba y, dabba f square upon dabba y dabba x, if you take either of them, the value should be the same, and that comes up to be 2x minus 4y plus 3. So once we find this, we can actually start with forming the Hessian matrix. So Hessian matrix will be equal to 2y, that is the dabba f square upon dabba x square here. After that, dabba f square upon dabba x dabba y here, dabba f square upon dabba y dabba x here, and dabba f square upon dabba y square here. So this becomes 2y, 2x minus 4y plus 3, 2x minus 4y plus 3, and minus 4x. So this is your Hessian matrix. We start finding the principal matrices. Principal matrices, like I said, h1 will be equal to 2y, just the first term. After that, go to the next diagonal element and entire square. So h2 will be the entire matrix. There are only two principal matrices over here in this problem. Now going forward, what we are going to do is we are going to find the determinant of these matrices at of h1 and h2. Like I said, if you look at the previous problem, these are nothing but x and y. So at extreme points, each extreme point, I'm going to substitute that value of x and that value of y here to get the determinant value. So x is 0, y is 0. The determinant of h1 will be equal to 0 and determinant of h2 is minus 9. So now, according to our condition, if they are either positive or negative positive alternating between them, only then they are definite. So right now here it is 0 and here it is minus 9. So this point is indefinite and hence it is called as a saddle point. Now if I put x and y, x is equal to 0 and y is equal to 0 in the function, I get the functional value, that is 4. Similarly, you do it for all the other points. So second point is 0 and 3 by 2. I get h1 as 3 and h2 as minus 9. So again, this is indefinite because this is positive and negative. We want negative and positive. Okay, only in that case it would be a definite. Otherwise, it is still indefinite. So this is saddle point again, and the functional value is still 4. After that, this is minus 3 and 0. That is the third point. The Hessian matrix is 0. Determinant of first principal minor h1 is 0. Determinant of second principal minor h2 is 49. So again, I guess this is not both positive because we have a 0 here, and that is why it is indefinite. So again, this is another saddle point. The functional value is still 4. If I go to the last point, minus 1 and half, I get h1 as 1, h2 as 3. Now both are positive, and by the definition, that means that the Hessian matrix is positive definite. Now if it is positive definite, at that particular point, we have relative minima. So at relative minima, the functional value is 7 by 2. So at this point, we can say that it is minimum. All right. So that is about your classical methods. There are a few charts that I'll look, and after that we can move towards brute search methods, that is grid search. Yes, there are a few charts that I'm going to try. Yes, anyone has any questions? Vishal Kadam has raised. Siddhant has a question. If you can type in, I'll be able to answer that. Siddhant, you're free to do whatever you want. Anyone else, any questions? All right. So with this, what I'm going to do is I'm going to go to the next part, which is a small part that I want to cover. It's brute search methods. That is the second method for optimization. Yes, there's still some chats going on. I'll just try to answer that. All right. So now the very small part that I want to cover. After that, we can go back to edit. The brute search methods, like we did in single variable optimization, there are brute search methods here as well in multivariable optimization, and I'm going to call them as grid search method. The first method that we're going to study is grid search. Now, grid search is a brute search method. Like by the definition, brute search means basically you're just putting the values of the variables and trying to get the functional values and then decide which is maxima or which is minima. So now it involves solving for the functional values using various values of variables. So basically, there are two variables, you take different values for them and try to get the functional values. And then you compare these functional values to see whether it's a minima or maxima. The variables are usually constrained. When I say constrained, what does that mean? Is that there is limit to a particular variable. So there will be a range given for a variable. So let's say if your variable is x, there will be a range given to you: maximum value for x, maximum value for minimum value for x, maximum value for x. Similarly, minimum value for y, maximum value for y. Your answer should lie between these two numbers. Now, this methodology involves keeping all but one variable constant and finding functional values by changing the independent variable by a suitable value. So basically, if there are two variables, x and y, you keep one variable constant, you keep x constant and keep on changing y by a suitable value and find the functional values. Second thing that you do is then you keep y as constant, change the value of x, and then find the functional values. So after all the functional values are found, you can find the maximum out of it and then get the answer. So now I'll just show you one example. We have find the maxima of the following function by grid search method. You have 16x plus 12y plus x square plus y square. The values for x, like I said, are constrained between 0 to -10. Take increments of 1. It should be -1. So take increments of -1. So this is the question that we are going to do. It's very simple to do. All you have to do is put the values of x and y here in this equation and get the answer. So now what I can do is I can draw a table on the top. I have x values that is going from 0, -1, -2 up to -10, and on y I have 0, -1, -2, -3 up to -10. So what I'm going to do at this point, I'm going to put x as 0 and y as 0 in the function and get the value. I get 0. Here what I'm going to do, I'm going to put x as -1 and y as 0, and I'm going to get the functional value, which is -50. This entire table I'm going to complete. Once this entire table is complete, the question was find maxima. So find the maximum value whichever is available, and that will be your maximum. It is very similar to your brute search method that you used in single variable, except that it was only one variable. Here it is multivariable. This method is suitable if you have two variables. If you have three variables, four variables, the method just keeps on getting tedious. So it's better to use this method only when there are two variables. So that is grid search method. It's a very simple method, and I just wanted to give you a brief of it. What I want you is you can complete this table and then find the minima and tell me the answer.